So I will talk about inducing schemes for piecewise expanding maps of Rn. And this is a project about, as you can see, maps of higher dimension which have discontinuities. So I'll start by giving you a very short introduction, which will be mostly general statements, just to give you the general picture. And then I'll give you a very specific setting and the main theorem, an application of it, and if there's time, some proof, a sketch of the proof of the theorem. So what are inducing schemes? Well, there are some structures, the existence of some structures in a dynamical system which you're interested in, if it has some chaotic behavior, can give you a lot of information about your system, starting from the existence of invariant measures, the number of them, maybe they're unique, up to more finer details about the system, like decay of correlations, finer statistical properties like the central limit theorem, and so on. And by an inducing scheme, I mean a way of constructing such useful structures. And these structures will contain geometric, dynamical, and combinatorial information about your original system. And if you're familiar with Young towers, a Young tower is an example of that. You saw it in the previous talk, in Dalia Terhesio's talk, where she mentioned a Young tower for a Sinai billiard in 2 dimensions. Remember that a 2-dimensional Sinai billiard has a one-dimensional unstable direction. Here we want to talk about multi-dimensional maps. So they're a bit restricted in the sense that they're expanding, but you can imagine them as being the unstable direction of a hyperbolic map with discontinuities, like a higher dimensional billiard. There are differences. So there are some things that you see here that you don't see in the Sinai billiard. And there are some things there that you don't see here, obviously the stable direction. So work on constructing Young towers for discontinuous systems are mostly restricted to 1 dimension. So if you know any construction of Young tower in higher dimensions, maybe you can tell me. I know maybe one, which is about the Vienna map, Alves-Vienna maps. Besides that, I don't know that many constructions. And also it depends on the Young tower. So here for piecewise expanding maps in higher dimensions, we can get a Young tower with exponential tails. This is the best kind of Young tower that you can get. So what is a piecewise expanding map? On the left, you see the graph of a piecewise expanding map in 1 dimension. It has several branches that are expanding, and you can see that these thin lines represent the discontinuities. Of course, in higher dimensions, I cannot draw you the graph of the function, but I can draw you what the map does. So the map, this is the phase space. It gets divided into several pieces. These pieces can be countable, so they don't have to be finite. It can be countably infinite. And T just maps each piece onto some other piece in the space. So these 2 blue polygons are images of 2 of these partition elements. They don't necessarily need to be convex polygons as I picture them here. They can have curved boundaries. They can be quite ugly. They don't have to be connected. Well, in this case, they have to be connected. But maybe higher iterates, they will be very badly disconnected. And so the dynamics is a map T on a metric measure space. But in this talk, I will focus on D being the Euclidean metric, M being the Lebesgue measure that you're used to, and X being a bounded Borel measurable subset of Rn. But besides this, since you can have many ugly domains to start with in Rn, I assume just this one condition about the space X. So in the previous picture, I pictured it as a rectangle. Usually maps are defined on rectangles as you see them in the literature, but they don't need to be, right? But if it's some ugly set, you at least need the boundary to be nice. You need the epsilon boundary of the space to scale like epsilon. And by boundary, I mean you take the topological boundary. This is the closure of X in Rn. intersection with the closure of its complement. And this is the set of points that lie within distance epsilon from the boundary. So if this is your set X on which T acts, then you want this is the epsilon boundary. Right? And you want the measure of this set, the area of this set, as you see pictured here, to scale with epsilon. You can allow for more general epsilon to the power of alpha, where alpha would be some kind of dimension for the boundary of the set X. But let's stick to epsilon to the power of 1. Yeah. So I need some more specific notation. So I denote by P the partition elements of the space X. So here you can see one of them pictured here, OH. And TOH is, of course, the image. And I will also denote by H the inverse branch of T, right? So it's just this branch, but yeah, the inverse of it. And I will assume that the push forward of the Lebesgue measure is equivalent to Lebesgue. So there is this Jacobian of this measure, which is just the determinant of the inverse branch. And I want to make 3 assumptions about my piecewise expanding map: uniform expansion, bounded distortion, and dynamical complexity. And these are, no, the partition can be countably infinite. So that is countable. The partition is countable. These 3 dots means countable. Of course, they can appear anywhere, right? They don't have to be right at the end. They could be in the middle and quite ugly. So uniform expansion just means that the inverse branch is locally contracting. So there's this epsilon, which gives you this local, means that you're looking locally only at points that are distant, within distance epsilon, 0, in the image. And you pull them back and they should contract. They should get closer by at least lambda. Lambda is less than 1. This is the worst contraction of your inverse map. And you want bounded distortion, which is a regularity condition on the determinant of the derivative matrix, or the Jacobian of the inverse branch. It just means that the Jacobian is log Holder. These are 2 standard, well, this is what it means to be piecewise expanding. Notice that if these are satisfied for the first iterate, they will also be satisfied with different constants for all higher iterates. And that if bounded distortion is not originally true for your original system, you can always divide it into, you can chop the space up and try to get bounded distortion on a finer partition. Since we allow for infinite partition, you can allow this with no problems. The dynamical complexity is this condition here, which I will explain based on this figure. So what it says, you're comparing the measure of 2 sets. So I'll explain to you what is the numerator of this fraction. So you start with some open set I, which has diameter less than epsilon 0. You intersect it with your partition element. So this is my I, the blue set. I intersect it with the partition element. It's this one here. So I get this piece with a wedge that I put a star inside. I map it forward under T. I get this expanded piece. I look at its epsilon boundary. It's drawn here. And I pull it back under the inverse branch. This would give me some boundary around here, around this wedge. But I will subtract the original boundary of I. So this part is not there. And I do it for all branches. So I will get some thickness around my discontinuity lines, which is pictured here as orange. So the orange is the numerator of this fraction. The blue is the denominator. It's just the lambda epsilon boundary of the set that you started with. And the sum of all of this should be related to the expansion in the system in this way. It should be contraction to the -1, -1, right? So this is a way to compare the boundary of the singularities to the boundary of the original set that you started with. Now, this may be at first sight, it looks complicated to check, but it's actually quite easy. And the trick is that you shouldn't try to calculate each of these expressions separately. You should just directly compare. And as an example, if you have any set in the plane, so this is your set I, and if your singularity is just a hyperplane, then the amount that this singularity contributes to the complexity expression, which is the expression on the left, is not more than the boundary of I itself. So the boundary of the orange, so orange, well, actually orange just for one partition element, right? So this part, let me call it A. The measure of A is at least the measure of the boundary of I. And this is not so hard to prove, right? Because if you have epsilon distance here, you can just move this amount of measure into the boundary of I. So there's at least as much in there.
You don't need to know anything about the image, how the image of I intersects with this context. You don't need to know anything.
No. I'm not. No.
The complexity is really just of the partition.
Yeah. But you go forward and then you go backward, right?
But forward you don't look
Yeah.
at where you
Go forward, you look at the epsilon boundary, and then you map back. So when you look at the epsilon boundary and you map back, you always map inside the lambda epsilon boundary of the pre-image, but it could be better. If the expansion is higher, you could get better. Right. No. This is one iteration. On the next iteration, of course, that one will be cut as well.
Sure, but your condition is just on that.
Yeah, the condition is just this. It's only on the first iterate of the map. Of course, you can replace your map T with Tn. Usually one expects the right-hand side to grow and the left-hand side not to grow. So it might be easier to check for...
But how much how important is that?
Yeah, because this gives you a better contraction rate. Otherwise, you will get only the worst expansion rate, or the worst contraction rate. But while here, you can get only the sum of contraction rates in the partition elements, which could be much better. It's a kind of local, well, it's what it is, I don't know. Yeah. So this is the complexity condition, and that's it. So that's all you assume about your piecewise expanding map in higher dimensions, and this is the theorem that you get. So if T is a map, as I explained, satisfying uniform expansion, distortion, and dynamical complexity condition, then it admits an inducing scheme with exponential tails. So what I mean by this is that there exists a refinement of your partition. So this is the partition, the thick lines are the original partition that I had for the 2D map. P prime is this refinement into open sets mod 0. And there's a return time or a stopping time. So on each piece, you define a time which is constant on the partition element. And you define this map, the first return map. So on each piece, you iterate the map, the original map T, by a different amount. So in this piece, you iterated for 2 times. In this piece, you iterated for 9 times. Here for 2019 times, and so on. And this will give you a map, which is a Markov map with bounded distortion, with finitely many images. And the tail of the return times is exponentially decaying. And if you make another assumption about recurrence in your system, then you can even get better inducing schemes. For example, you can make this return map to be full branched, but on a smaller subset of your space, Z. You can make sure that the greatest common denominator of the return times is equal to 1. And sometimes you can get even better. You can ensure that there is at least one piece of the space with return time equal to 1. And this can be very useful. If you achieve these the first two items, this will give you a Young tower with exponential tails. Application is some non-uniform, going from getting information about non-uniformly hyperbolic systems. So let's skip that. This is some advertisement where we treated an example. This is a 2-dimensional non-uniformly expanding map, which is not Markov and not conformal. In some directions, you expand exponentially, some direction polynomially. And then you can get sharp results. It's a work with Ian Melbourne and Sandro Vaienti. Okay, advertisement finished. Proof of the main theorem. So let's not read that. Let's look at pictures. So on the left here, this is your set X, on which you want to construct the inducing scheme. So the first thing you do is you just chop it up into rectangles, the very small ones. I can tell you how small. There's some delta. You have to chop it into pieces smaller than delta. And the good thing about this delta is that your dynamical system will expand each piece to pieces that are much larger than delta. So let me tell you how to make the inducing scheme on one of these objects that you get by chopping into rectangles, right? So I put a star in there. I drew the same part of the phase space here. If you can do it on one, then you will be able to do it on all the other ones. And since the set is bounded, there are only finitely many of such sets. So whatever you do on this part, you can do uniformly on the other ones as well. It's just a finite set. And so that's, again, the set that I had drawn down there, right? The partition that we want to focus on. This straight line is part of a discontinuity line. It doesn't have to be straight. I just want to show you what the dynamics does to it. So the dynamics cuts this piece into several pieces and expands each one, as you see it's pictured here. But on average, it expands it to a much larger size than delta. There will be a lot of small pieces delta, but there will be at least one where it's much larger than delta. So it has to contain one of the original partition elements that I started with. This is the part, this is when I stop. I stop here and I define, there is some set in my original piece that I started with, which maps onto this rectangle. I stop here and I define tau to be the number of iterations it takes to cover this rectangle. And I remove this little piece which mapped into, it doesn't have to be a rectangle, I just draw it as a rectangle. This one is for sure a rectangle, but this one, no, this could be some ugly set that maps onto a rectangle. So I stop here and I define tau to be equal to, say, 10. That means in 10 iterations, it just covers this. Now there comes the big problem, right? I need to repeat this. So I need to show that I can repeat the same with whatever is left over. And this is what's happening behind the scenes. There's a way you can control the size of sets to make sure that whenever you stop, what is left over is also a nice set. And by nice, in this system, niceness is a sort of condition like the condition we assumed on the boundary of X. So nice sets are the ones where the boundary of X scales like epsilon. These are sometimes, well, I call them like epsilon regular sets. And what's interesting is that in Rn, an epsilon regular set must contain an open ball of radius epsilon. Right? In this picture, you can just see it here. If you take this point and you take an epsilon ball, it has to be contained in X. Of course, I mean, this is just a bounded measurable set, but this is true in general in Rn. So there's this notion of size, which is very, very helpful, and is invariant under your dynamical system if you just assume the complexity condition, which kind of tells you that you don't cut that often compared to the expansion that you have in your system. So once you have the complexity condition, bounded distortion, and expansion, you can ensure that you can always repeat this picture. Right? So whatever is left over, you again iterate. Again, it will map onto some rectangles. You stop them, and then you continue. Since you can do this in every, say, 100 iterations, and you can remove a fixed amount, a fraction of measure at each time, these are all bounded. This means that you get exponential tail, right? So you have a fixed bound on the number of iterations it takes for you to be able to do this again. You get a fixed bound. Obviously, you get only finitely many images because there are only finitely many pieces in your system. And if you have some recurrence, you can improve this to have the properties that I mentioned before. So thank you for your attention.